Well, good morning, good afternoon, good evening, everyone. For those of you who are joining us for this webinar, this is the March installment of the San Diego Big Chapter, which includes Solid State Circuit Society in webinar. So hope everyone's staying safe. We're hoping to start live events, hopefully in the coming months as things are opening up, and that we hope that you'll be able to join us for that. So today, moving on to the main event, we're absolutely honored to have Professor Sudeep Sekar, my friend from University of British Columbia, my hometown, where I also did my studies, and I'm quite jealous that Sudeep can afford to live in Vancouver. Anyways, with that said, just a quick introduction about Sudeep. So he received his bachelor's from the Indian Institute of Technology in Kharagpur, and his PhD from the University of Washington. He has worked previously in industry at Intel Labs for some years, and very accomplished individual, also very generous with his time to help us with ISSCC technical committee, as well as running the Vancouver Solid State Circuits and CAS chapter. Besides being a good friend of mine for some years now, Sudeep, is a distinguished lecturer, and so this is a distinguished lecture webinar. So with that, I'm sure folks would much rather hear you talk than me. Sudeep, thanks so much for your time, and we look forward to this really interesting talk.
Thank you, Alvin. Thank you, Jeff. Thank you for hosting. Okay, I'll get started, and thank you everyone for coming to attending the talk. So I'll talk about silicon and how it can be a playground for both electrons and photons. So the people who do the work and who make all of this happen are listed here. So I run a lab at University of British Columbia, and I have students working on silicon photonics, on clocking and RF and millimeter wave, and then several students who have graduated and collaborators at UBC and around the world, and the funding agencies who sponsor our work. Are you able to see my cursor, Alvin?
Yes, I can. Yeah. If you want to turn it on to
laser
pointer mode, that might be a little bit more obvious. Yeah.
Okay.
Thanks.
Yeah, I'll do that once I start using it. Okay, so here's the outline. I'll start with the motivation behind the talk, and then I'll give you a very brief introduction to silicon photonic devices, and then jump into the circuits, and then go over some case studies, one for transmitters, for high-speed transmitters, one for biosensors, and one for photonic accelerators. So if we go back and take a look at how the CMOS technology advanced over the last 40 years or 50 years, and how packaging helped this as well. Now, we started off with transistors. We started off with transistors on the CMOS process, and then we quickly added resistors to control the gain of an amplifier, and then added capacitors. And then towards the 1990s, we started to add inductors and started to do RF integrated circuits. So all of these are essentially manipulating electrons, resistor, capacitors, inductor, transistors. And then something else that also helped the design was packaging. So whatever we could not build on a chip, we can put it on a PCB, and we have electrical wire bonds that we can connect to off the components that are not on the IC on the board. And then hence we could start adding things such as crystal oscillators for PLLs and antennas that we couldn't put on the chip. So all of this, just to give you why I'm presenting it or talking about it, is we'll see that how the photonic equivalent of this is how that is evolving, and how they can be both merged together. So if you look at the the evolution of the silicon foundry. The first foundries showed up in very early 1980s, and then the designers had access to a PDK, and they could design circuits and not really worry about device level details on a day-to-day basis. And then in around 1990s, RF CMOS came, and then around 2000, CMOS SOI foundries, so silicon on insulator foundries, came as well. Had a lot of RF applications for that. But then if we look at the reason for all of these evolution is, of course, we try to improve the performance of electronic circuits. So we want to make them faster, reduce the latency, increase the parallelism, and we also could miniaturize discrete electronics or bulky components on a chip. And then finally, we enabled many new applications, and of course, this community knows about it. Now, all of this, again, is a playground for electrons. So we are manipulating electrons. And then around 2010-ish time is when we started to see foundries showing up that leveraged all the investment that we have already done in CMOS SOI process and started to do photonics, integrated photonics on a CMOS SOI process as well. And that opened up a playing field for photons to be manipulated as well. And in the last 10 years or so, we've made giant leaps in the sense that now circuit designers have access to a PDK that they can depend upon, they can trust upon, and they can use photonic components and electronic components together to build circuits and not necessarily have to tweak each and every device at the photonic level. So with silicon photonics, we can do similar things that we did with electronics over the last 30, 40 years. So first of all, we can complement electronics. So photon, because of the speed of the photon, speed of the light, we could accelerate some of the functions that electronics is slow at. We could reduce latency, and we can increase parallelism by using multiple wavelengths of light. So we can build transceivers, and for high speed links, we can use photonic accelerator. We can make massive switches instead of electronic switches, having optical switches. We can also miniaturize discrete or bulky optics. So instead of putting a LiDAR on the top of a Humvee, which is massive, we can design solid state LiDARs, which are few millimeters in the dimension on each side. We can design some of the world's best filters. And then we can enable new applications such as biosensors and also doing quantum computing with photonics. So just quick discussion about optical fiber. There's a difference between fiber and integrated photonics, but fiber is the conduit for a lot of transceiver applications. So unlike copper, optical fiber has very low loss, right? So we're talking about loss. We measure the loss in dB for kilometers for a fiber, and it also has a very low frequency dependence. So as I'll show you in a successive slide, that means that the intersymbol interference is much lower than copper if we're talking for a given distance and for a given loss. Also, the optical signal within fiber and waveguides are not susceptible, very less susceptible to crosstalk and EMI. You can put a lot of wavelengths in the same fiber and hence enable wavelength division multiplexing, and that helps in parallelism. And finally, the cable management is easy. So if you're talking about data center, these are thin fiber cable, and you're not talking about massive copper cable, so cable management is easy. So the main driving force behind the advent of silicon photonics and commercialization of silicon photonics is the fact that we have data centers mushrooming all over the world now. And if in the cartoon on the right hand side, so if we look at data centers that are situated far apart from each other, hundreds of kilometers apart, we use optical fiber to connect to them, and that's how photonic transceivers started to come into the play for these long haul and terrestrial links. But then when the data centers are co-located next to each other, within a few let's say 80 kilometers or so, or within a data center itself, when we have to connect racks of servers to each other, that's when silicon photonics is really seeing a big play, because this is a high volume market, and cost is of concern as well, and we know that CMOS shines there. So a quick primer that ultimately the data in a transceiver application is still electronics. So we want to send high zero electrical data from the transmitter, and the receiver would like to detect the same data. But if I'm looking at a copper channel, the transfer function of the copper channel, so plotting gain as a function of the frequency, or S21 as a function of the frequency, there's a frequency dependent loss. And for certain channels, there could be a lot of resonance as well. And what it does, it creates intersymbol interference. So the signal, the nice and clean ones and zeros, are not only attenuated in voltage domain, but they also mix with each other, and that causes intersymbol interference. And this behavior increases when I'm sending more and more data rate, or when I'm increasing the length of the copper channel. And yeah, we can throw equalization at it, but it consumes a lot of power. So beyond a certain distance, it makes sense to use optical fiber, and beyond a certain loss, it makes sense to use optical fibers. So let's look at quickly at an electro-optical link. So again, I want to transmit electrical data. So I have some electrical transmitter, and I want to detect the same electrical data as for an I/O. Now, if I look at the fiber, okay, well, I need to somehow take this electrical data and put it into the optical domain so I can transmit it over a fiber. So we start off with a laser, just a continuous wave laser. The carrier frequency is about 250 terahertz or 270 terahertz. And then we design a bunch of optical circuits. So we design a modulator, and we connect the laser to the modulator with some kind of a connector or a coupler. This modulator, the goal of this modulator is to take the electrical data and somehow convert it into an optical modulated data. So whenever whenever I want to send a 1, I'm going to send my light, and whenever I want to send a 0, I will not send any light, ideally. And then this modulated data is again coupled to the fiber. On the other hand, we have another coupler, and then we launch this data on a photodetector, and the photodetector converts this optical signal into an electrical signal. In order to do this modulation, we need a whole bunch of electronics, a whole bunch of CMOS circuits. So we'll take the electrical signal, we'll we buffer it, and then we'll send it to a driver, which drives the modulator. And then, because of the fact that optical circuits are temperature sensitive as well, we need a CMOS controller often to make sure that we compensate for variation in temperatures and variation in process. On the receive side, once I have my electrical highs and lows, I need to amplify it. We use a transimpedance amplifier. And the reason it's called transimpedance is that the unit is from current to voltage, hence the transfer function is instead of an impedance. Then we buffer it and send it to my electrical IOs. So conventionally, these were all built with discrete components, 3-5 components, expensive gold box. And with the advent of the data centers, we want to shrink it into a small transceiver that we can plug in at the back of the server. So everything, this is a transceiver from Intel, where we have the electro-optical transmitter, the optoelectrical receiver, the laser, isolators, everything is in a small form package. So what I'm going to be talking about is silicon photonics. So how to build these modulators, these photodetectors, couplers, connectors, all on a silicon SOI CMOS process. So we would want to use silicon to route, to quote unquote make the silicon wire to route the light, as well as silicon to do any optical processing or switching. Now, once we have used the CMOS SOI process to do silicon photonics as well, there are two ways I can have the photons and the electrons play with each other. The photonic circuits and the electronic circuits play with each other. A very popular way is to take the CMOS SOI process, let's say a 90 nanometer SOI process or 130 nanometer SOI process, and design the photonics on it, and tweak the process in terms of the stack to make it very good in for photonic applications. So we would design our modulators and detectors and all the optical components on one CMOS SOI process, but it will not have the electronics. And then we design the electronic drivers and the TIAs in a CMOS process or a BiCMOS process, and then we can flip chip all of them on a transposer here as shown, or wire bond them. The nice thing about this is you have chosen the best processes for doing electronics and photonics, and you can choose a FinFET process for electronics or a BiCMOS process, and then you choose the best process for photonic. Another option is to use a monolithic process. So for example, GlobalFoundries has a monolithic process. You've got electronics, photonics, all in the same process, and it helps in eliminating parasitics, ESD, reducing ESD, and so forth. But of course, you have to make compromises in the sense that, well, if you look at today's offering of GlobalFoundries, it's in a 45 nanometer SOI process. So you have 45 nanometer CMOS transistors. So if you have a lot of DSP to do, probably not the best platform. Okay, another question that you would often hear, another myth, is that photonics is going to change the world and take over electronics. Well, that's not going to happen. Especially as somebody who does both, we have to make sure that we understand the advantages and disadvantages of both technology. So if I want to modulate, design a modulator in a photonic circuit, even the smallest modulator fits in hundreds of micrometers. Okay? Whereas we can fit 100 transistors in 1 square micrometer. So there's a huge difference in the size. Now, if you come from the optics world, you would look at this modulator and say, oh, wow, this is very, very small, because you're coming from the optics world. But if you come from the electronics world, you're like, okay, this thing is huge, and we better make sure that we use it where it makes sense and not use it where it does not. So for example, I don't envision silicon photonics being used for on-chip connection where the trace lengths are small, because again, it's not worth it. It's too big. But for chip to chip, or for definitely from box to box, it makes a lot of sense. Okay, so I'm going to quickly go over silicon photonic devices. For all of this is in a silicon photonic platform. So we've got waveguides, which guide the silicon light. Then we have splitters. So these are, if you're coming from microwave world, you know what a 3 dB power splitter is. This is exactly like that. So it's a 3 dB splitter. Even the waveguide, because you're carrying 273 terahertz signal, these waveguides are less of a wire and more of a transmission line, because you're transmitting very high frequencies. And then you have combiners. So again, 3 dB combiners and couplers and so forth. So going to the waveguide, this is your SOI process. So we've got silicon substrate here on the bottom here, and then we have silicon dioxide. So that's the insulator, and we have the silicon as the guiding medium, and then we have another oxides as the cladding. So another silicon dioxide as the cladding. Now, if we couple light into this waveguide, then the most of the light is contained in the waveguide. And this is because the refractive index of silicon, 3.47, is much higher than the refractive index of the silicon dioxide that is surrounded with it. So it causes total internal reflection, and the light is contained in it. And you want the light to be as much contained as possible, because that means you're not losing photons and you're not increasing the loss. There is an application where you want the light to leak in slightly, and it always leaks. A little bit of light would always leak. And I'll show you later is how we can actually make use of it for designing biosensors. How do I couple the light into a photonic circuit? Always been a tricky problem, but it's getting easier and easier. So we can, for example, just like pads that you put on the periphery, you can do edge couplers. So you can take an optical fiber and couple it to your chip using edge couplers. Or you can just like a flip chip pad, which can be put anywhere on the surface. You can use a grating coupler, which essentially acts, if you're coming from again from RF world, these are a bunch of arrays of antennas, and you can put this grating coupler anywhere on the chip and put light in or out of the chip. Something that's coming up now, which I believe is going to make the life of testing photonic circuits much easier, especially for CMOS people, is photonic wire bonding. So now we have photonic wire bonding as well. So if, for example, if this is your silicon chip, you can put these quote unquote pads, surface pads, wherever you want. And then let's say this is your fiber, the photonic wire bonding machine goes in and just couples the fiber from here to here. So again, once this is there, you can imagine that how, just like electrical wire bonding changed the way we did system design, photonic wire bonding is a big technology that has come up recently that we believe would help the coupling problem significantly. Okay, so next we'll talk about the silicon photonic circuits. Specifically, I'm going to talk about what we call a micro ring resonator. So micro because it's very, very small. And another one is a Mach-Zehnder interferometer. And these are somewhat bigger devices. So how does a ring resonator work? It is a very, very high quality notch filter. So the quality factor of these could be 5,000, 20,000. So the way it's designed is we have input light coming in on a straight waveguide, and then we also design a round waveguide, a ring next to it, and we do not make this ring touch the straight waveguide, but we design this interface as a directional coupler. So as the light goes in, it can couple into this waveguide, and this directional coupler introduces a 90-degree phase shift. Then as the light propagates around the ring, it accrues phase shift. It's accruing delay. Delay is phase shift for a continuous wave. So it's accruing phase shift, and then as it comes out, it sees another 90-degree phase shift. So now, if you look at total phase shift around this path, for a specific wavelength, so the phase shift is a function of the wavelength. If the phase shift going around the loop is some multiple of 2 pi, 360 degree, then we have 360 degree plus a 90 and plus a 90, so 180. So for the original light propagation and the light propagation around this loop, you have 180 degree phase shift, because we can ignore the 360 degrees. So net 180 degree phase shift additional that this device gives. So for that specific wavelength, you will get destructive interference. The original signal and the signal as it goes around the loop will be out of phase, 180 degree out of phase. And then for those specific wavelengths, as plotted here on the x-axis, the output will be null. So the transmission, if I plot the transmission in terms of dB, the output would be gone. But for the rest of the wavelength, there is no destructive interference, so the output you will not see any difference in the output. And hence, you've made notch filters which are very sharp, and they're also repetitive because the 2 pi would be accrued for every integer multiple. Another device is an interferometer, again uses interference, constructive or destructive, where you take the input signal and you split it half and half in power, or if you like to talk about it in terms of electrical field, you split it as 1 over square root of 2, because remember, intensity is proportional to the square of magnitude of electrical field. So if it's a 3 dB intensity splitter or power splitter, it's 1 over square root of 2 of electrical field. So you split this, you have a 3 dB splitter. In one of the arm, you introduce a phase shift, and I'll talk about that, how is that done. And what it does, it takes the input field and adds an additional phase shift. And then you can add them again as a 3 dB combiner, and the output is the sum of this signal and this signal. And if you do some math, you can show that output intensity is equal to the input intensity that you're launching into this Mach-Zehnder, half of that multiplied by this 1 plus cosine of phi term. So this makes it interesting because now if phi is 0, I'm not doing anything in this branch versus this branch. If phi is 0, then the output intensity becomes equal to input intensity because this term becomes 2. If phi is 180 degree out of phase, then this term becomes 0 and I get a null at the output. So again, by playing with phi, I can do a constructive or destructive interference at the output. And what that means is that I can design modulators out of that. But first, the question is, how do I introduce the phase shift? Again, learning from the silicon world, we can dope the silicon waveguide wherever I want to make a modulator, and p-doped, n-doped. And by doping them, the silicon, we can introduce additional free carriers. So we can introduce holes or electrons or holes. And whenever you add additional free carrier in silicon, the movement of photon, the movement of light changes, sees a different refractive index, and that introduces a phase shift. And thankfully, this is quite linear. So the more carriers you inject, the more phase shift you get. And we know that one way to inject, to manipulate carriers electronically is to apply a voltage in a PN junction, and that will change your carrier concentration. So by applying a voltage, I can get a linear phase shift at the output. So if I have some input field, electrical field at the output, I will get a linear phase shift as a function of input voltage. However, these PN junctions, these doped waveguides have some excess loss as well in amplitude domain. So if you had some amplitude here, you'd get a loss, like only a fraction of this is seen at the output. But this phenomenon is very fast. I mean, we can modulate, we can apply a 50 gigahertz signal here and modulate the movement of electrons and holes in the junction diode, and hence can make very high speed circuits out of it. So the way we build a modulator, again, is to dope, let's say, one arm of this waveguide. So these are all diode, and this is typically a millimeter long. So, and hence these are distributed diodes. So you can, so because the output intensity is a function of the input intensity with some cosine of the phase shift, and the phase shift is a function, is directly proportional to the applied voltage that on this junction. We can plot the transfer function of a Mach-Zehnder modulator as a function of the phase shift or as a function of the applied voltage. And this will be nothing but 1 plus cosine terms. So it looks something like this. So if I apply very high voltage, as much as what we call a V pi voltage, then that makes this term pi, and hence the output amplitude, optical amplitude drops to 0. We call that an optical 0. But if I apply a very low voltage, almost 0 voltage, then this term cancels out and I get an optical 1 at the output. So by modulating my electrical signal for highs, lows, and highs and lows, I can get optical highs and lows, and hence we made a modulator. And just like we apply an AC signal on top of a DC bias on a transistor, we bias this electrical signal at a certain position, so that which is right in the center of this transfer function, and this is where I get 3 dB power from the 3 dB lower power from the optical 1, so half of the power, and we often call this a quadrature point, quadrature biasing. Okay, so now I've talked about enough devices. I'm going to talk about how we make a system out of it. How do we make sure that my photons and the electrons are playing together really well? So as far as the Mach-Zehnder modulator is concerned, the limitation of the bandwidth that we get is often from RC parasitics. So these are a whole bunch of distributed diodes over 1 millimeter long device. So you have lots of parasitics. And how do we solve this problem? Well, instead of driving them as lumped element, we design these electrodes as transmission lines. So try to absorb some of the capacitance. And then we design the driver, the CMOS driver, to drive this transmission line. And for that, we need, because we're talking about 40, 50 gigahertz, we need to make sure that the terminations are all matched. So we'll design this electrode as a 50 ohm transmission line, and then we'll make sure that the driver side has a source termination of 50 ohm, as well as we terminate the end of this transmission line with 50 ohm as well. Now, if you look at the overall optoelectrical bandwidth, so let's say I design a driver with 50 gigahertz electrical bandwidth, and this circuit had a certain 3 dB bandwidth as well. So what's the overall optoelectrical bandwidth, and what dictates that? So of course, what dictates that is the fact that how good is of an impedance matching you have, number one. What is your driver electrical bandwidth to begin with? But also, as the RF signal propagates on this electrodes as well, it's also going to see attenuation. So that also limits your overall optoelectrical bandwidth. And finally, you have the optical wave going in, and you have the RF wave going on top of that. So you need to make sure that as both of them are going together, they're aligned, they're velocity matched. So so that's one final constraint that you have. You need to make sure that the two waves are propagating and they're velocity matched, so that the voltage that the wave sees as a function of distance is the same, and hence all the interference is lining up. Okay, so now I'll next go into the case studies. Let me just make sure how much time we have. Okay. All right, so I'm going to first talk about high-speed transceivers application. So how do I design a driver for this Mach-Zehnder modulator? So I'm going to first look at two-level, so PAM2 case, NRZ or PAM2 case. So I have my optical signal going like this and combining. But for the electronics, what I'm concerned about is these transmission lines are essentially a 50 ohm impedance. So instead of driving single-ended, I'll drive them differentially because we know differential is better. So I have, for example, this differential driver. So P and N and some tail current source, and I do termination on the source side, and we also do termination on the load side. So RT is equal to Z naught of this transmission line. And then if I apply a signal, let's say a 1 at this end and 0 here, so differential signal, so this transistor is off, and the current is essentially propagating in this branch, and it's propagating like this. Okay. On the other hand, if I switch the input signal, then this transistor is off, the current flows like this and like this into this transistor, this branch. So we can prove that the peak-to-peak differential voltage, electrical differential voltage, is nothing but RT-IT. Okay, and we would like to be it as big as the pi voltage that introduces a complete 180-degree phase shift in the relative arms of these two Mach-Zehnders. Or if we can't do V pi because we're perhaps limited by the voltages we can have on a CMOS chip, as high of a V pi as we can. And the PN swing goes from plus RT-IT by 2 to minus RT by 2. And hence the total swing peak to peak is RT-IT. Now that we have managed to apply electrical swing on this modulator arms, then that would create an optical modulation at the output. So you sense continuous wave, but because we're modulating this at the output is going to be high and low and high and low. So you'll have a certain high power and certain low power, and hence you build a driver for the modulator. Now, this driver design is not easy because we would want to increase the swing onto this driver, but to increase the swing, if I increase, RT is limited, right? RT is limited by matching 50 ohm requirement, so we cannot play with RT. So to increase the swing, I have to play with IT. But if I increase the IT for a given supply voltage, these transistors can go into the triode region. So that's not good. If I increase the VDD, well, then I have reliability and breakdown concerns, because if I crank up the VDD so I can increase IT, but then that means I also, so that I have large voltages here, I need to make sure that the transistors are happy. So typical high swing drivers, often you'll see lots of similarity with, for example, power amplifiers or high swing drivers in wireline links, in electrical links. So, for example, you can use techniques such as cascoding. You can use thick gate oxides. Thick gate oxides add a whole bunch of parasitic capacitance. So you can use shunt peaking techniques to compensate for that effect. So a lot of techniques that we've already learned we can leverage for high swing driver designs. Okay, so what I earlier told you, the example that I've been talking about so far was for two-level signaling, PAM2. But of course, we'd want to do more advanced modulation because so that we can cram in more and more symbols in a given amount of electrical driver bandwidth and the optical modulator bandwidth. So we'd want to do PAM4, QPSK, maybe QAM16, so that I can have 4 times the spectral efficiency, or I can cram more bits in a given bandwidth. So how do I do both amplitude and phase modulation using a Mach-Zehnder modulator? So let's build it one step at a time. Let's say if I want to do PAM4, I can design a PAM4 driver. So I have 4 levels of amplitude here coming from the driver, and at the output, when we apply it on the modulator, we'd get 4 levels of optical signaling. Okay, but of course, now we need to make sure that this driver is linear. So not only is high swing, but it's also linear. Okay. In order to do phase modulation, we again play a trick in bias. So if I had my Mach-Zehnder modulator as shown here, instead of looking at intensity that I have been looking so far, where intensity, you take the electrical field modulus and you square it. So you throw away the phase information. But if I want to do phase modulation, I want to keep the phase information. So let's look at the electrical field instead of the intensity at the output. And the electrical field looks something like this as a function of the applied voltage. And you can see that it's correct because if you take the modulus of this red curve and square it, you're going to get this black curve. So now if I look at this electrical field, I'm going to bias my modulator not at equal point, but at 180-degree phase shift. So I will bias it at what we call the null point, where I don't get any optical output. So if I bias it at the null point and I apply my electrical voltage, highs and lows, around this null bias point, then as I go to higher voltages, I get a certain electrical field, but it's negative. And for equal but opposite excursions in the voltage domain, I get the same electrical field magnitude, but opposite phase shift. So these two are relatively, and this is positive and this is negative. So now I can do phase modulation. So if I apply a PAM2 signal from an electrical driver, at the output of the optical modulator, I'm going to see phase shift keying, equal but opposite intensity or electrical field. For example, if I wanted to do a QPSK transmitter, I'll take one set of modulator and a driver and another set of modulator and driver. I'll apply PAM2 signal to both of these drivers, and then I'll take so that's essentially creating 2 PSK signal. So this PSK signal is here, and the same PSK signal is here. And as far as the optics is concerned, I take the optical power, split it half and half, split it half and half, combine and combine. But we add this additional 90-degree phase shift in the optical domain here. So what this is going to do is it's going to take this 2 PSK and rotate it here into this 90-degree into quadrature domain. And once we add them together, we get QPSK signal. Of course, we need 2 modulators and 2 drivers. Well, we can do better. We can have PAM4 electrical signaling and hence get a 4 PSK constellation in the optical domain. And this time, in these 2 drivers, I apply PAM4 signals, and that would give me a 4 PSK in I, and after 90-degree rotation, a 4 PSK in Q, and I can add them together. And this is how we built almost a half a terabit per second coherent transmitter, and we presented at ISSCC a couple of years ago. So I got my 4 PSK here, 4 rotated 4 PSK here, so I have my 16 QAM here. Okay, but because light has polarization as well, I can copy paste the entire circuit again and get another 16 QAM, but then I can use what we call a polarization splitter and rotator. So you can have X polarization and Y polarization. Remember, these are all transmission lines, so X polarized and Y polarized, and I can rotate one of the polarization into Y domain, and at the output I get dual polarization. So this is working at 250 gigabit, this is working at 250 gigabit, and then the output you have 500 gigabits or so. So again, light gives you much more freedom because you have amplitude phase, but you also have polarization. You have multiple wavelengths. You can copy paste this entire transmitter multiple times, acting on different wavelength of light, and then you can still add them up together onto the same fiber. So parallelism, speed are two huge benefits that we see in a transceiver application. Okay, so now I'm gonna quickly take a look at my time. Okay, so next I'm gonna talk about accelerators. A lot of the applications in data center today are driven by inference and training. Okay, and if you look at specifically for inference, there's something that's repeatedly being done is multiply and accumulate, right? So if you look at a neural network, there's a lot of multiply and accumulate going on. So if you look at digitally, if you have two operands x and y, you multiply them and you accumulate them together, that is your MAC, multiply and accumulate. Now, if you look at, let's say, a 64 by 64 MAC, and if you implement it in a fancy digital CMOS process, the overall latency for this MAC system would be, even if you're running the clock at 2 gigahertz, is about 100 nanoseconds. Okay? And this is often too much for inference tasks. So can we do it faster? And this is where photonics shines, because now you're talking about speed of light. Of course, the latency would be very, very small. So how do I do multiply and accumulate with photonics instead of digital? Well, we'll have to rely on analog photonics, not digital. So we would take our digital signal, and so let's say I have my two input electrical wave, E1 and E2, and what I want to do is multiply and add them together. Okay, so these are already modulated information for X and Y, and so they're already modulated. Well, I know accumulation and analog and photonics is nothing but combining, so I can bring two waveguides together and close to each other, and they will start to interact with each other and add up. And multiplication, I can do multiplication as some kind of a phase shift here, and then I'll add them up together to add them up again. So we can implement multiply and combiner, or multiply and accumulator in analog photonic domain, and this will be, the speed would be limited by the speed of the modulator to begin with, which is 50 gigahertz, not 2 gigahertz. And the bandwidth, of course, is very, very high. So if I look at a photonic MAC network, so in this illustration here, you have a bunch of Mach-Zehnder interferometers, and you are doing it with your photonic MAC. Well, the latency now is 3 orders of magnitude smaller than digital CMOS. And the bandwidth is, let's say, 1 order of magnitude higher than digital CMOS. And the power consumption is large compared to digital CMOS, but only because you're taking into account the laser power and the bias control power. And as far as this power is concerned, this is zero power. But again, I mean, we as a system people, we know that we need to capture the power of everything. We need to capture the power of high-speed DACs and ADCs that also go in taking the digital signal and converting it into analog, so you can modulate your optical signal really fast. So here's a photonic accelerator that was recently shown by a startup called Lightelligence. So this is their photonic MAC. Okay, and this is your light coupled into it. And as you can see that they claim 5x speed improvement compared to the NVIDIA GPUs. Again, because it's not 100x, because you have lots of ADCs and DACs as well, right? And they add latency as well. But again, photonics here, you've got your photons playing here, lots of electronics, drivers, TIAs, coprocessors, and so forth, all of them in a PCIe card format. So again, use photonics where it makes sense, reduce latency, improve speed, but use electronics where it makes sense in doing a lot of other tasks that photonics is not good at. Okay. Taking a look at my time. Okay. All right. So the last example I'm going to talk about is biosensor, and it's actually very relevant to San Diego. So if we look at how we can use a chip to make a biosensor. If you recall earlier, I had told you that as the light is propagating in a waveguide, not all of it is self-contained. Some of it leaks as well to the surface, and we can make use of this to make really sensitive biosensors. So imagine again that I have some light launched into this tray in this waveguide, and I have a ring resonator next to it. So these are coupled to each other. Okay. Now, if I plot the transmission as a function of wavelength for this ring resonator, if you recall, this was a very, very sharp notch filter. Okay. Now, imagine that I added some analyte. So let's say this is a blood that I'm flowing over this chip, and it has some COVID particles. Okay, these COVID particles are going to attach to the surface of my ring resonator, which has some, let's say, binding receptors to make sure that only the COVID particles are attaching to this surface. When these particles attach to this surface, the refractive index will change, because remember, some of the light is leaking. So the refractive, as these bindings happen, the effective refractive index, overall refractive index changes, and that changes the notch frequency of this filter. So by measuring the notch frequency, the movement in this resonance, I can track if there is binding that's happening or not. I can track also the kinetics of this binding, because as the wavelength would shift slowly, I can even figure out, okay, what is the kinetic of this reaction. So the real-time monitoring of refractive index can be done due to the fact that the light is leaking in an evanescent mode out of this waveguides. So there's a company out of San Diego that has actually commercialized silicon photonic biosensors, and the company's name is Genelite. And so they sell a printer-sized machine with the cartridges, and these cartridges have these really small ring resonators. So these are small chips we are talking about, and because these are again photonic-wise, these are small. So we're talking about let's say 30 micron diameter, and you can put multiple of them, and you can, let's say you have a whole bunch of sensors here, okay, and as you are sending fluid on it, and as the bindings happen, you can detect presence and absence of a certain molecule, but also how much of that, the concentration of that. So this gives you a quantitative reading for the biosensor. Okay, so what we are at UBC are working on is trying to shrink the Genelite system. So the Genelite system uses silicon photonic chips, so very, very small ring sensors. But the rest of the system is really big. So because you are essentially using a filter where the x-axis was wavelength and the y-axis was transmission, in order to sweep that wavelength, a tunable laser is needed. Okay, and so the laser wavelength is tuned as a function. So you sweep the wavelength. But these tunable lasers are really bulky, and they cost $10,000 to $50,000. So the chips are very cheap, CMOS scale, but the lasers are bulky and expensive. And because they're bulky and expensive, and you want to send a wavelength into this ring as well as this ring as well as this ring, so you need this robotic nanopositioner system to shine light into this ring and detect, then move this and shine light into this ring and detect. So this system is also quite complicated and bulky. And finally, the detectors are also bulky. So yes, the chips are small, but the whole system is bulky. And being CMOS designers and circuit designers, we could add complexity to the chip to make the whole system small. So instead of having a tunable expensive laser, we can use a $1, not a $10,000, a $1 fixed wavelength laser. Okay? And instead of having the nanopositioners system, we just use photonic wire bonding. So we take the DFB diode, the laser diode, and photonic wire bond it to my silicon photonic chips, and then just use a whole bunch of splitters to guide the light into multiple rings. So split the light and put it into many, many rings, and then put photodetectors again on the silicon photonic process, and then CMOS electronics to shrink everything. Now, because this is a fixed wavelength laser, instead of sweeping the laser, we can also sweep the resonance of the ring as well, because we know that the resonance of the ring is a function of the phase shift, and I can sweep the phase shift using electronic signals. So this entire thing is the size of a credit card instead of a printer. So here's the Genelite machine, and here's our design. So the entire thing is on the size of a credit card, and of course we've added a lot of complexity in using electronics and photonics, but this is where complexity really belongs, on a chip, not on the laser and discrete electronics. So we have photonic circuits, we have TIAs, we have ADCs, we have DSP to track everything. And so this is the work that we are doing. We're currently testing this chip, and hopefully we'll be able to share some results later this year. Okay, so to conclude, the silicon photonic is ready. The PDK is ready, and if you are a circuit designer, you can start using it. You don't have to be a device engineer, and you can pick a two-process technology, TSMC and a photonic process, or you can pick Global Foundry, where everything is together, and start building circuits. And we are right now, there are lots of low-hanging fruits in the photonics world, unlike in the CMOS world, because CMOS world has been around for 40 years, 50 years, and the photonic world is only, as far as the PDK is concerned, realistically 5 to 10 years. And we can build really into clever and useful circuits that help us complement electronics, make discrete optics smaller, or come up with new applications. And the reason for that is not only you have all the electrons, like resistor, capacitors, inductors, and so forth. Now you can also use polarization of light, and you can use intensity and phase and manipulate all of that to build systems that combine multiple domains. So I talked about transceivers and sensors and accelerators, but a lot of exciting work is going on in phase arrays and LiDARs, and in signal processing, solving NP-hard problems in gas sensing and quantum computing and so forth. So lots of applications in a lot of fields, but we have to be smart about using photonics where it should be used and using electronics where it should be used, and figuring out where the complexity should go. So at that, I will stop. Thank you.
Hey, Sudeep, thanks very much for this excellent presentation. Just a reminder to folks who are online, if you have a question, please type them in the Q&A panel, and we'll address them. Meanwhile, I have several questions I want to ask you. So in the demonstration where you actually use different light polarizations to effectively double the information you're feeding through the optical fiber, I didn't catch how you actually get the different polarizations, and not just how you transmit the polarization, but also how do you, on the receiver side, also filter the right polarization, the two polarizations, in order to not to basically process them independently, and how is that done?
So thankfully we don't when we take the light out of these laser source, they already come with polarization. Polarization is an innate behavior of the laser. So we have dual polarization light coming in all the time, and often we throw away one of the polarization because we have optimized our photonic process, that's the SOI process, to handle one kind of polarization. So if you notice, when the signal that comes in, we essentially, what we do is two polarizations are coming in, and we first, okay, actually I've not shown here, we first split the polarization so that they're both in what we call transverse electric mode, which is what my circuits are built for. And so this is exactly two parallel circuits, both in transverse electric mode. But then just before launching back into the optical fiber, which can carry both the polarization, we use another circuit, which is a polarization splitter and rotator, which essentially what it does is it takes the TE polarization and moves it into like essentially it takes X polarization, both of them X polarization, and moves it into a Y polarization. So this is done at the very end of the chip before you launch the signal back into the fiber. And then on the receiver side, I've not shown the receiver side here. Again, when the signal comes in from the fiber, you first again split it into two polarization, because again, your receiver is also optimized only for the TE mode, transfer electric mode. So you split this and then you copy paste two receivers in parallel, one of them handling the TE signal, but one of them handling what used to be the TM information into the TE signal. And then you again replicate, have two parallel chains of photodetectors, transimpedance amplifiers, ADCs, and so forth.
Okay, so this is where I'm a little bit confused. In the beginning, on the left of the diagram here, where you split the two polarizations, how is that done?
Oh, so this is a passive circuit that we design where again we play with the waveguide dimension to be able to change the light that's coming in into dual polarization into two TE modes.
Okay, I see. I see. And so the receiver circuit will look something quite similar to that, because
Similar.
you've got,
Yeah.
well,
So imagine if this was your receiver, light was coming in, you would have again a polarization beam splitter this time, and that will split it into two transverse electric mode, and then you'll put a photodetector and all of those TIAs and everything.
got it. Okay. Another question. When you listed the different types of modulators, you mentioned obviously the Mach-Zehnder modulator or interferometer, and also, of course, the ring resonators. But in the past, I've seen electroabsorption modulators being pretty prevalent as a potential type of modulator that's substantially smaller, but it has, of course, like what extinction coefficient or extinction ratio concerns and so forth. What's the state of EA modulators or electroabsorption modulators relative to these two that you've highlighted here?
Yeah, so I described Mach-Zehnder modulators. I did not describe Mach-Zehnder micro ring modulators, right? I talked about micro ring resonator as a filter, but you can imagine that if it's a filter, we can also add a phase shift here and modulate it at really high frequency, right? So that also is being used. Intel is working on it. NVIDIA has publicly talked about it. Ayar Labs is commercializing it. So those are micro ring modulators. And the nice thing about it, they're really, really compact. You can drive them just as a capacitance. You don't have to deal with transmission lines, so you save a whole bunch of power. Now, electroabsorption modulators are interesting, but the use case for them are limited. So most of the electroabsorption modulators are built on silicon germanium. So this is your silicon CMOS process. You add some germanium to it, and but they only work at a wavelength at 1550 nanometer. So they only work efficiently at 1550 nanometer wavelength, which is what we use to connect long haul, like our metro. So talking about hundreds of kilometers, interconnecting data center. Whereas within a data center, we mostly use 1310 nanometer wavelength, and there the electroabsorption modulators do not work so well. There are people working on it. For example, IMEC is working on the recently published a 1310 electroabsorption modulator, but there's still a lot of work that needs to be done there. And because the industry already has a momentum now on 1310, it is really hard to change that. I mean, we already have optical fibers in data centers that are doing carrying 1310, right? So again, that switch you have to now convince the industry to move towards 1550 or come up with better electroabsorption modulators that work at 1310.
I see. So it's related to basically the the wavelength of the light relative to essentially the band gap of the electroabsorption modulator material, right?
Yes, yeah. So it's this device limitation that people are trying to overcome, but there's still more work to be done.
Got it. Okay. So folks, if you have more questions, some questions, please share them in the Q&A panel. Okay. Oh yeah, we have one question that just came in. Are there standards for silicon photonics communications? And also a second part of the question, in terms of testing, is the technology mature enough for silicon
So
photonics?
yes, so there are standards. So OIF is the standards body and that helps with the standards. So for example, there's a standard called DR4 for data centers, and they don't necessarily pick silicon photonic. They say, okay, well, an optical transceiver has to meet these specifications, and you could be like an indium phosphide kind of company as well, try to play in that space. But yeah, there are standards that you need to have, this much loss and this much extinction ratio, and the eye diagram should look like this, and and the laser power should be this, for example. The second question, is it mature enough? So if you look, so Intel, for example, is shipping millions of transceivers, right? And other companies like Cisco, for example, is also like Cisco and Intel are the two big players right now in the transceiver market, and then they're all both silicon transceivers. So if you look at uh, yeah, so they're shipping a high volume transceivers now. So definitely these are reliable processes because the PDK is mature. Um, and this is where we have to be careful. So a lot of optics people are physicists at heart, and they like to tweak the device and to make the device better, the optics of the device better. Whereas a lot of circuit engineers and CMOS people are circuit engineers, right? So they want to have a reliable PDK, some like a modulator, a photodetector that's already been manufactured. You have Monte Carlo statistics for that, like variation statistics for that, and you want to use that and not worry about tweaking the device itself. So not worry about tweaking the transistor, if you will. You want to reliably use the transistors and make circuits with that. So we have PDKs like that now.
Got it. So, one thing, we talk, I guess the plasma effect. I mean, that to me, I kind of internalize as the electro-optic effect, right? Where basically the refractive index is the free carrier plasma dispersion effect. I kind of just lump that as an electro-optic effect, where basically the refractive index is a function of carrier density, right? But the other thing also, I mean, in a product, um, or just not just a product, but just any link, invariably there's going to be temperature gradients and temperature self-heating effects and so forth. And as we know, there's also a thermo-optic effect where the refractive index is also a strong function of temperature and so forth, right? And so, I mean, given the state of the technology, the silicon photonics technology right now, there has to be some sort of calibration that accounts for self-heating. And I'm also hearing, I mean, it's possible to actually basically build heaters near these modulators to basically use that as a control knob also. But somehow there has to be some sort of a feedback system to make sure that the temperature is stable. Otherwise, your carrier path, your differential carrier path, or sorry, differential optical path is going to not give you very good extinction ratios and the filtering, et cetera. You know where I'm going, right? So what's the state of the thermal feedback technology and so forth to actually make this very, very productizable?
So as you were mentioning, right, not only but just by doping the silicon with P or N, we can change the phase shift. We can also heat the silicon. So we just put a metal next to the silicon waveguide, so a metal trace, M1, let's say, and we send a current into that metal, and because metal will have an I square, the joules heating, it will heat up, and if the temperature, local temperature changes, then the waveguide, near the waveguide also has a phase shift, which is a function of the power that is being dissipated in the heater. So but we use this technique to also manipulate the phase of the signal, but this is a slow effect, right? So you have to move heat in and out. Hundreds of kilohertz is typically what you can get out of it. But thankfully, it doesn't introduce any loss in the optical domain. So there's no loss here, unlike in a free carrier dispersion where there is a loss in the intensity as well. So you have to be careful about this because, of course, you don't want to waste power, right? I square R power is a parasitic effect in electronics. Here you're using it to a certain extent, so you have to be careful. But this is where again electronics shines, CMOS shines. In fact, I should be restricting it to CMOS. That we know, like we can. These are low speed. We know how to design 10 bits, 12 bits of ADCs and DAC at kilohertz, right? So we can easily control the resolution of how much current we are putting in a heater with a very high accuracy. And we can also design, so we can detect, because these are control circuits and what they require is high resolution ADCs and DAC, and we can design that. So CMOS is actually a very good match with photonics to be able to control the temperature effect of the photonic. Now, devices like Mach-Zehnder modulator are significantly lower in sensitivity to temperature variation, and that's why the industry loves them. Most of the high volume product today is Mach-Zehnder modulator, whereas ring modulators are more sensitive, right? Imagine these are quality factors of 5,000, right? If you have a quality factor of 5,000 and the temperature changes by 0.1, 0.2 degrees Celsius, it is going to move. And so you need an accuracy, a DAC and ADC that would detect even, let's say, a 0.1 degree Celsius change. But we've built that in the CMOS world for a long time. So again, because these are slow speed effects, we can compensate for that. And that's what our lab is commercializing and other companies such as Intel and NVIDIA are looking at.
So on the topic of size, you talked about how big these optical devices are, right? And then clearly one of the limitations that contributes to the size of this, for instance, like a Mach-Zehnder modulator, is the fact that the electro-optic coefficients are not that high, right? If you go to a more optically lucrative material like lithium niobate, you probably can make you need less distance to create that phase shift, right? So related to this, given that, for instance, Intel has shown that in its products, it's doing hybrid bonding of materials, etc., where you can introduce more optically desirable materials for the purpose of building this. I mean, do you see that there's much of an opportunity to really make things a lot smaller, or it's not really warranting the complexity of the manufacturing?
So I think, so I'm smiling, Alvin, because I know you're also a device physicist at heart. So I think again, this is we can either live with what has already been QA'd by the foundry now, and we have a Mach-Zehnder modulator and ring modulators. We know all of the statistics for it. Go build circuits with it, or we can ask for quote unquote better transistors, right? Like, oh no, give me a better device, right? And we can put effort into it, and that will take 3-5 years to again commercialize in high, or at least qualify in high volume. So that's definitely a path that a lot of photonic device people are engaging with. But again, then you are waiting again for several years before this transistor equivalent is ready for you to build circuits with, right? Specifically, lithium niobate, yes, they have better modulation efficiency. You can make them smaller, but introduction of lithium to a CMOS fab causes contamination issue. So we'll have to solve that, and you'll have to convince these foundries to solve that problem. Integration of indium phosphide is also difficult, not as difficult, I imagine, as lithium niobate, because, for example, Intel has already shown that you can add this to make lasers. But then again, a lot of work needs to be done at a manufacturing level to do that. And certainly, I can imagine germanium silicon modulators or electroabsorption modulators or indium phosphide modulators added to a CMOS foundry. There are challenges that can be solved there, there's also polymer modulators. So these are organic polymers that you can add. Again, much easier to add to the CMOS world. But yeah, that again requires several years of manufacturing change and quality assurances.
Got it. Sudeep, one last question to close this. Really appreciate your time on this Friday morning. This is related to scaling. Is there such a thing analogous to an optical Moore's law that guides, how things are to be shrinking? Or, my guess is probably not, because you're limited by essentially the wavelength of light you're using, right? And if you try to reduce the wavelength too much, you get to a point where basically everything will fry, right? But I want to hear your thoughts.
Yeah, it's a good question, and thank you, Ying, for asking this question. It depends how which definition of Moore's law you believe in. The way the Moore wrote it, which was about economy, right? Cramming more and more transistors makes it cheaper, right? Or are you thinking about Moore's law in terms of nanometer transistor length, right? So definitely we see more and more and more photonic devices being built on a given chip, and you can plot year versus number of devices on a chip and how we are cramming devices, and it is going up. But as on the other side, if you look at the technology scaling, that is limited. For example, you can ask, right? In the interest of time, I didn't talk about it. MOSFET was invented around 1960, I think 1959 or 1960, right? And laser was invented in 1961, the semiconductor laser. But the electronic revolution happened much early, right? And the photonic industry, the integrated photonic industry, is only here for 10 years. Right? What happened? And one thing that happened was optics has a certain carrier frequency, hundreds of terahertz, and we need to be able to contain it on a process. So we had to wait for lithography for the CMOS world to really give us 180 nanometer CMOS or 130 nanometer CMOS, where it made a lot of sense to start doing silicon photonics. It was very hard to do it before that. But at the same time, going to 22 nanometer, or like right now we are at 45 nanometer in the CMOS SOI silicon photonics, but does it make sense to go to 5 nanometer? Does it make sense to go to 20 nanometer? We again have to look at, okay, can I contain all of my light in the waveguide with the stack and be able to not lose the information, as well as does it make sense to spend that much money on that, on advancing it further? So definitely, because we're dealing with really the carrier frequency of a laser at 1310 or 1550 is in 200s of terahertz, we have to make sure that the process is meant for that.
I mean, there are also considerations with voltage too, right? I mean, these photonic devices need a lot of voltage, and high voltage are general, and advanced technologies generally don't talk to each other well, right?
Yeah. So Mach Zehnders typically would want 3 volts, sometimes even 5, and ring modulators you can live with 1-2 volts. So yeah, but indeed, voltage requirements are also a concern.
Yeah, I mean, even 2 volts is just completely not friendly at all with anything, like maybe 5 nanometers and onwards, right? Yeah. Cool. Well, hey, Sudeep, thanks again for your time to share with us, enlighten us on a Friday morning here in the U.S. For those of you elsewhere dialing in, appreciate your attendance, and stay safe and well. And we wish you could be coming here to San Diego. You're always welcome here, and we'll definitely need to find an excuse to get you out here, and I definitely will look you up when I'm back home.
Thank you, Alvin. Thanks, Jeff. Thanks everyone who's still dialing in.
Yeah. Okay. Great. Okay. Have a good weekend, everyone. Take care.
Take care. Bye.